Welcome back, everybody, to my second lecture in this mini course. So in this one, I'm going to look at computing using quantum walks. So yesterday, I basically set the scene about what computing is and isn't, and how to think about when computing is efficient, and other aspects to do with it. And so today, I'm going to look at what that means when you want to use quantum walks for computing in both an abstract and an experimental setting. I'll start with kind of the historical approach to it. So people were starting to get excited about quantum computers back a few decades ago now. There were some clear and obvious algorithms that almost immediately became quite famous. So it's clear that simulating quantum systems, one of the original motivations, is going to be a potentially useful thing to do if we can build quantum computers. Some of the very early, more computer science-like algorithms, as Deutsch-Joscher, and then quantum Fourier transforms, which underpin Shor's factoring algorithm and many other algorithms. And which we've already heard some things about, Grover's search of an unsorted database, which is a canonical, it's a basic problem type that can be applied to many, many different actual problems. And you can see we're mid-late 90s here when these algorithms appeared. But then it was only a few years later that people started to look at quantum versions of random walks with algorithmic intentions. And so these papers appeared in Stock 2001, on the archive in 2000. And you see Andris Ambainis was involved in both of these seminal papers. He's now a professor in Latvia, for those that don't know, and still works from time to time on quantum walks in a computer science algorithmic setting. So why did people jump at quantum walks so early on? So this essentially is why, if you look at classical algorithms, randomized algorithms in particular, are essentially based on classical random walks. What you find is they're very widely used, especially in physics for simulations. They underpin quantum, any kind of Monte Carlo simulation you might do, anything with Markov chains. And those can be applied to quite directly to particle physics calculations, quantum chromodynamic simulations. You can get completely different length scales. You can model the motion of polymers, the way they might behave in a fluid, or in engineering processing of them. You can model how surfaces grow, like crystals grow when their crystal is coming out of solution, for example. Many body systems, another obvious place where these kind of models based on randomized algorithms will do the work for you. And then you look in computer science and you'll find that the best classical factorization algorithm is a randomized algorithm. Satisfiability problems, approximating the permanent of a matrix, and graph isomorphism, which we have heard quite a lot of talks on. Again, the best classical algorithms are, in a sense, randomized based on classical random walks. So the computer scientists went looking to see if a quantum version of a random walk could give them better quantum, in other words, quantum versions of algorithms for any of these important problems. So here is basic definition of a classical random walk on a line. And I've done it in what I've called a recipe. I've done an algorithm for it rather than the equations for it, because I want to make clear what it is to have an algorithm rather than just write an equation. So algorithms, even if you're not really a programmer, if you can follow a recipe for cooking, recipes are algorithms, right? They're instructions for how to do something. Start with an input, your raw ingredients, and you get an output, a finished baked product or meal or whatever. And you can see, so this is, as I say, like the input, and a set of instructions that you do in order. And some of them are deterministic. You toss a coin, you get an output. And then some of them are conditional on previous steps or conditional on the situation. So it might be check whether it's starting to brown. If it is, it's done, take it out of the oven, right? And if not, leave it for 5 minutes longer, then check again. So you get loops and you get decisions and you get repeats. Maybe not this many repeats in a recipe, but it's the same idea. So this is a recipe or an algorithm to do a classical random walk on a line, because we'll keep it simple, but clearly you could do it on any other structure and it would come out much the same, except you'd have to decide how to move to different places in the structure. And if you do this, of course, and repeat it many times, you will start to sample from and build up the probability distribution of the position after t steps, and it's a binomial. And it has a standard deviation that's the square root of the number of steps that you took. So now if we look at this algorithm, and we now want to do a quantum version of it. So we'll add the quantum bits like this. So the first step is the same. We're going to start at the origin. Now you want to toss a quantum coin. So that'll be a qubit, because we just need two choices again. And I have written the equations here because it's a Hadamard operator, a unitary operator on a single qubit. And what it does is produces the same result except for this sign here. So now we have our conditional operation. We're going to move according to the state of this coin, but it's quantum. So now we can move left and right. We don't have to choose. We can do both. So there's our shift operator, and the zeros are going to the left and the ones are going to the right. And then we toss the coin again and repeat. So the remaining steps are the same. And we can't possibly get outside plus and minus t in this setting of 1 step per time step. Repeat it, and we'll end up with a probability distribution when we measure the walker. So you can see straight out from that this is a reasonable translation from here to here in terms of what you're doing to make it quantum. And what you get, of course, is a very different distribution. So this discrete area function with 2 lobes, and it's spreading out linear in time, in the number of steps compared to square root for classical. And it's analytically solvable, and this is where some of the first solutions were presented in those stock papers. So that's nice, and you're looking and going, yes, but they look very different. Are they really sort of 2 ends of the same process, if you like, one quantum and classical? And if you interpolate between them by doing intermediate measurements, if you like, or making it less and less quantum, they do indeed go from one to the other. And it looks like this. So down come those spikes, and up goes that central peak. And you get a nice transition between the two for different probabilities of measuring at each step. And what I noticed back in 2002 is that in the middle of this, you get a nice top hat distribution. And if you're a computational physicist like me, that's great because it lets you do uniform sampling. But now I can do uniform sampling over this linear range, linear in the number of steps, instead of having to do it with the random walk, which would give me a square root range here, and I'd have to deconvolve the binomial to make it uniform. But that we can do, and we often play with the distribution that we use for sampling. in order to bias it to sample unlikely events, and then we undo the bias because it was a controlled one that we put in there. So the fact it's actually a neat top hat is not so important, but it's helpful because we don't have to do a complicated deconvolution to take the area function out of it. That it's a non-trivial result in some sense, you find out if you put if you only measure the coin at each step, you don't mess with where it is in position. So you only measure part of the state, not the whole state. And if you do that, instead of getting that nice flat, at exactly the right level of decoherence, what you get is that the spikes are still coming down when the central peak is still going up. So it does a much more messy interpolation. So it still goes between the two, but it's not a neat top hat that you get out of this here. So that was actually seen earlier in this paper when they were modeling noise for an experimental proposal. So we have what we're happy is a quantum version of the classical random walk, and now we can take that and do the quantum equivalent of building algorithms that is done with classical random walks. And so, of course, we can do search. It's very related to Grover's algorithm, a reflection about the mean. And that was proposed right around the same time by Shenvi, Kempe, and Whaley. And here it is in recipe form again. So this time we're not starting at the origin, we're starting in a uniform distribution because we don't know which node is marked, and so we'll make all the nodes equally likely. And now you have to use a coin that is multi-dimensional, so it has more than two choices because you can't get a speed up for search on the line. There are no-go theorems for that. So D is the dimension, is the number of different choices we have at the degree of each side. And this is what the coin looks like. We can make it any dimension we like. It'll be have more entries here if D is larger. So then we run it for this approximately this many steps. So there's a square root in here. So we get to be faster than random guessing, which would be n, or n over 2. And now with high probability, not necessarily 1, the walker will now be at the marked node. And so there's your quadratic speed up. And the neat thing to think about here is it's kind of the inverse of starting at the origin and trying to get that uniform distribution. So here we started at the origin, and we did a number of steps and some decoherence, and we got this far out. So that's just kind of a rough analogy, if you like, but quantum mechanics is reversible, and so it's a perfectly valid way to think of it. I don't know how, if I want to find out how to get a particular output, you can start with that output and now try to run backwards and see if you get an easy to prepare input state, and whatever you did is reversible, and to get there is reversible enough that you can run it the other direction. So that's a different intuition for what's happening in Grover's search. And indeed, if you keep running it, it will spread back out again to its original distribution and then come back to the marked state. So it does indeed oscillate, and you do get that reversibility. But of course, if you're doing an algorithm, you won't want to run it any longer. You want your answer in the shortest time possible. Okay, so this is now very promising because we've got one of the basic important quantum algorithms, and quantum walks can do that almost as a natural. How about something a little harder? Because quadratic speed up is nice, but the complexity theorists really like the exponential speed ups. And so again, very similar timing in 2000. arrives the first proof of principle that you can get an exponential speed up with a quantum walk algorithm. But it's in a kind of weird problem. So we have this binary tree graph, and another one, a copy of it here, and then you have lots of random edge connections here, such that all of these central nodes are degree 3, but these connections in the middle are random. And you have 2 special nodes, an entrance where you start and an exit where you're going to get out. And I'm going to label this by the columns of how far into the tree we are or out the other side. Was done using a continuous time quantum walk. That's not necessary, and I'm going to show you on the next few slides. It's easier to understand what's going on if you use a discrete time walk. But the particular authors working on this were much more used to proving things in continuous time walks, where you can use Green's functions and a whole bunch of other stuff. But it does make their paper quite hard to follow, because they spend more than half of the paper proving that the continuous time walk can be efficiently simulated on a discrete time quantum computer. None of which is really to do with the problem, but it's just to do with putting all the pieces of the proof together. So I'm going to give you a different picture of how it works, and I'm going to save continuous time quantum walks for tomorrow's talk. First of all, here's a picture of it in action. This is actually continuous time along here. So this is a simulation of their algorithm. And we start here at the entrance. So these are the columns along here, but there's more columns here than there are in this picture. There's only 4 here, but there's 10 here. And it goes off steadily through until it gets to the center. That purple dotted line is the glue here. Then at the glue, most of it goes straight through, but a little bit of it gets reflected and comes back. So you can see it's slightly lower amplitude here. And then you get a good sizable peak out at the exit at precisely the right time here, and the time depends on the hopping rate. So the time units here are quite arbitrary in the sense. And then if you let it keep running, if it reflects here, it starts to come back, but messy, because the dispersion is now breaking up the wave packet that went all the way through nice and neatly like this. Okay, so that's what happens in pictures. Here it is with a coin, where it's easier to understand what it takes to make an algorithm out of this. So first of all, you need an oracle to hold the graph description. If you could see the whole graph, you could see how to get through. So you're only allowed to have local information here. If we've got labels on our vertices here, for example, B or W, whatever, and we randomly assign edge labels, say E and H, and their H, so which edge is labeled 1, 2, 3, and we randomly assign each end of the edge a label 1, 2, or 3. So those random labels are no help to a classical algorithm. They've got to make sure that they describe this so that a classical algorithm can't find an easy way to do it. So what you do is you give the oracle a vertex edge pair, and what you get back is a pair of labels on the other end of the edge. So if I give my oracle B and E, what I get back is W and H, such that EH is the edge joining vertices B and W. Notice the oracle is its own inverse. So if you feed the oracle the output from B and E, what you'll get back is B and E. This is important because, as I said, quantum mechanics has to be reversible, and so we need reversible operations here. So we can set this up as a unitary operation in quantum mechanics. It's actually the shift operation for this walk. If you apply G to a position and particular edge, what you'll do is you'll find yourself at the other end, at W and H. So our quantum computer has two registers, one with vertex labels and one with edge labels. And we're starting the state that is the input node. So input is entrance, and it's got two possible edges. So we're going to be in a superposition of going along both of them. So I for 2 and 3, and the root 2 is for the normalize the quantum state. Then we apply the oracle shift, and then we'll apply a degree 3 Grover coin operator. So that's the same as I showed you for Grover's search, but I've got d equals 3 in this. And that gives you a third off the diagonals and minus 2/3 down the diagonals. Now you need a way to know when you get to the exit. So you can recognize it because it's only got two edges like the entrance. And so you need a few little tricks depending on what you allow your oracle to do. The first one is you don't apply the coin operator if you're at the entrance node. And you know what that is because you started there and you're allowed to remember what that much. So you recognize if you get back there and you don't apply the coin operator. But you don't know how to recognize the exit. But if the oracle is about to return something that isn't part of the graph, it will instead give you an error code. Right? So if you ask it for the edge that doesn't exist because it's the one that would lead out from the exit like this, instead it'll give you an error code and you go, aha, I've arrived, I made it. And then you can test for the error code to identify the exit. So this is the discrete time version of it. So that's the columns along here, and then the probability of being at that particular column summed over all of the vertices in that column. So this is the step number down here. So after 8 steps, we've reached the glue, 9, 10, and by 11 steps, you can start to see that some of it got reflected and some of it is going forward. And then you've got these two pieces heading backwards like that, and a reasonably high probability of getting out at the exit here. Good. So we've now got several algorithms for quantum walks. And quantum walks are established for the computer scientists in complexity theory as a tool they like. They can prove things about it. And they've got algorithms with quadratic and exponential speed up. So there's lots of work going on where quantum walk search becomes a subroutine in a bigger algorithm, or looking at variants of search, for example. But with the computer scientists getting all excited about this, the experimentalists started to think about implementing quantum walks too. In fact, they'd already implemented, even without knowing it, photonic quantum walks. And there've been lots more by different groups at different times. Many more than this. This is an old slide. If I updated it, I wouldn't have room to fit the half of the experiments on here now. Some of the other proposals, not all of which have been done, is to put it in the phase of a cavity field kicked by an atom, and that walks you in a cycle. So that was a relatively early one in 2003. You can use the vibration states for an atom in a trap, and you can think about atoms in optical lattices, which is, again, 2002. It was a good year for quantum walk development. And then 7 years later, Karski et al., which is Dieter Maschida's group in Bonn, implemented this and in a science paper. So the question is for us, now we're thinking about how to compute with quantum walks. are any of these experiments, these implementations, actually computing, or could they compute? So let's go back and remember from yesterday, we're doing science, and what we want is to get a good theory with a small enough error between theory and measurement out of our experiments. And if we have a good theory, we can do prediction, and then we can build technology, including computers. So we can probably tick this box that the experimentalists are really good at their stuff. And they really have produced very nice quantum walks, except they're quite noisy, so that they're more like the ones I showed you with, if we go back and find the pretty pictures. So they're more like they don't always get the pure spiky distribution. Sometimes the spikes are degraded, and they're a little more heading towards the classical, depending on how long they run them for. But that's okay, because we can model that. And so we have a good theory of that, and we can match up and say how noisy it is. How long do we run it to get that nice top hat? So we could do our uniform sampling. So I think we tick this box. Now, how efficient are they is the next thing. We've got our polynomial scaling with system size, maybe. We certainly got answers on human timescales. The experiments are running in the lab very fast, so we don't need to worry about this one so much. But we do need to worry about whether we're getting more efficient than classical computers. So here's our computer diagram again, and we want our quantum walk. If it's going to be an experiment, it's going to sit down here. And then our theory of quantum walk will be how we map it here and how we map it here. But then we need to do some encoding here and decoding. And encoding matters a lot to efficiency. It determines the physical resources we require. So if we want to encode numbers, we could do a unary encoding. So these little spots are deliberately like vertices in a graph, because if we do a physical quantum walk and we build the graph, that's we're going to have little spots like this for our numbers. And then here's binary, and it doesn't look too different until you realize that there are only a logarithmic number of bits compared to the number of vertices we've got. And then we look at the readout. So if you want to do a unary encoding and you want to find what your output is, if each one of your spots on a graph is a different number, you've got measurements with n outcomes. Now for binary, you make log 2 measurements and they've got 2 outcomes each. And 2 log n is a lot smaller than n. So you have a lot less measurements, and discriminating between them is a lot easier. It's exponentially better for precision. If you want to double your precision, you add 1 more bit. If you want to double the number of n to 2n, that's doubling the size of your experiment, not 1 more bit. So we've got a reduction in memory here. So this is very general. Doesn't have to be binary, but we usually use in qubits. We could use qubits if we wanted. And classical computers have even another layer of logarithmic encoding with floating point numbers, just to remember that. This trades precision for memory, but means we can represent much larger numbers in fewer qubits or bits. Right. So implementations of quantum walks that are actually in qubits in a quantum computer register, before IBM Q came online, there was actually only one that wasn't a physical quantum walk, that was actually encoded in qubits. And that was done in 2005 in an NMR computer, and they had 3 qubits. 1 they used for the coin, and 2 to encode the position. And they did a cycle of size 4, which is more than they have qubits. So this is definitely encoded, right? And if you do a quantum walk on a cycle of size 4, it turns out to be periodic with a period of 8 time steps. Quite a lot of small cycles can be exactly periodic. That will be a diversion, but there's quite a few more papers looking at periodicity, perfect state transfer. They're all closely related concepts on finite graphs. IBM Q came online. Anybody could try implementing a small quantum walk in those in their chips, and they did. And you can't do very many steps. They're very noisy, and it disappears into random output quite quickly. Some of my students have done this. We haven't published it, but it was a very useful exercise in understanding just how limited the first quantum computer chips are. So let's look, if we're building bigger quantum computers or bigger quantum walk experiments, let's look compare quantum and classical. This is the ultimate test of have we got a useful quantum walk implementation from the point of view of building a computer. So if we do a walk on the line, the classical limit, if you really push it and use lots and lots of parallel processing, you might get 2 to the 34, which is 10 to the 10 steps, which is an enormous number. Just on a laptop, you can easily do, say, 10 to the 8, 10 to the, or something like that. Quantum computer doing this would need just 35 qubits. So encode the 34 here is the number of qubits you need to represent numbers that big in a quantum computer. And then one more because you need a coin if you're going to do it on a line. If you were going to build a physical quantum walk experiment, you would need on a line, you'd need 2 times 10 to the 10 sites, which is crazy. If you want to do a high dimensional one, then it looks a little more reasonable. And if you want to do quantum walk search, of course, you need to be 2 dimensions or higher anyway. So let's go down to 2 to the 24. So something where 24 qubits would do. And 2 qubits for a coin, because if we're doing a grid, we now have 4 choices of which way to go. So that needs 2 qubits. Then the square root of this, pi by 2 square root of that's about 6,000 steps. Okay, that's a more reasonable number than 10 to the 10 for steps. And if we arrange the sites in a 3D grid, we're getting down to a 256 cubed grid and something more like 2,000 steps. So in a physical quantum walk experiment, about 16 million is what 2 to the 24 is. That's a lot of sites to construct, but it's not unfeasible. Maybe photonic walks could do that. You could laser write that into the kind of silica glass that they use for waveguides. However, current experiments are more like 50 to 100 sites. So we're not even within striking distance of a physical quantum walk being anything like the numbers that we can just simulate easily in a laptop. So this is why the encoding matters. If you have good coherence and you have 40 qubits, you could do a bigger quantum walk than you can do in your classical computers. But if you wanted to build it as a physical walk, that's a huge undertaking. Just as a little bit of an aside to make sure that we've got the different levels of abstraction clear here. Here's a little table of physical systems versus algorithms run on computers. And we've got examples of random walks, classical and quantum. So if we have a quantum walk in a physical system, it would look like a particle in an optical lattice, for example, which I'll show you on the next slide. Classical example, Snakes and Ladders is a board game. I'm not sure people outside the UK know this one. So Google it, look it up. You'll find you can play it online if you like. If we want to run our quantum walk on a computer, then we might do the glued trees algorithm I was discussing. If you want to run a classical random walk on a computer and do something interestingly useful, you might do a lattice QCD calculation. Now that all sounds really basic and straightforward until you realize that you can also do a classical computer simulation of all four of those possibilities. So for example, I did simulations of this, which I just showed you, the output from the graphs. And particles in an optical lattice, that paper that proposed that was the one that did the coin-only decoherence and produced the not top hat graph. I just told you to go and look up snakes and ladders and play it online. Well, that's a classical simulation of it, right? And this one, which seems like the strangest thing to do, a classical computer simulation of a classical computer doing a lattice QCD calculation, that's actually the most scientific one of them all. There is a published paper on this. The lattice QCD people are pushing the development of high performance computing, and they got in collaboration with IBM, they were making some dedicated processors for doing the simulations. And so what do you do in order to program it? You don't just wait for the hardware to turn up. You do a simulation of it, virtual machines. Virtual machines are now everywhere. If you use a cloud computing, you will very likely be using a virtual machine. One computer simulating another computer for you so that you can have it entirely to yourself. But really the hardware is doing that for 10, 20, 100 other people at the same time. So we have multiple levels of abstraction in what we run on computers, and it can sometimes be a little bit tricky to keep those clear. So now we're ready to talk about quantum walks being universal for quantum computing. So this is Andrew Child's result from 2008, published in PRL, I think in 2008 or 9, not sure. And then I ran a summer project with a PhD student, Neil, and several undergraduate project students. And we worked out, so Andrew Childs did the continuous time walk version of this. And we thought, that's a great puzzle. We'll work out the discrete time version. So we did, and published it in PRA. But the real result is Andrew Childs. And what he did, it's not about proving you can implement quantum walks, physical implementations. It's about proving that you can efficiently implement the quantum walk on a quantum computer. So the key phrase from his paper is any sufficiently sparse graph. So the graph needs to have a description that's logarithmic in the number of sites in order to be efficiently implemented on a quantum computer. It characterizes which Hamiltonians it's efficient to simulate. And there is more work from Dominic Berry et al. On that topic, published around the same time. So to illustrate what that means, these are pictures from this paper from the discrete time version, because it's easier to see what's going on with that. It turns out the gadgets you need, basically what Childs did is he took a circuit, or all the elements of a circuit model quantum computing. So we're going to, these are our qubit states. Our input state is usually a product state. They're often zero state inputs. And then we apply gates either to single qubits or to between two qubits like this. So these are just examples. There's nothing special about what this algorithm does. A couple of controlled NOT gates and a phase gate, just to have something to illustrate with. And then Andrew Childs translates that into a graph on which the quantum walker walks. And the nice thing about this result is it becomes ballistic. So you create the graph that represents the circuit you want to execute. You start the walker off on some sites that represent the input nodes. And then you just press go and it runs. And you don't have to do any other control because it's all there in the structure of the graph. And then after a suitable amount of time, you measure at the other end. So it's also a demonstration that quantum computing can be done ballistically, that you don't need to have active controls doing each gate one step at a time. So, but this is what the graph looks like for the discrete time version. So that simple circuit here, 3 rails, 4 gates, 3 qubits, has turned into this graph for the quantum walk. I have an exponential number of rails, sites. We have 1 for each amplitude, each possible state of the 3 qubits. And there's the Hadamard gates applied to each of them. This pair is 1 C0, swapping zeros and ones. This pair is the other C0. And there's the phase gate here, which is done by doing something different other than this wire here. So what's this chain-like piece of the wire is a way to use a 4-dimensional Grover coin. If the 2 inputs have the same amplitude, it will pass it through. So it just acts as a, and if they're not, it will oscillate, going round like this. So even and odd will give you inverted versions of it. So it's a way to do transport. And Andrew Childs, for the continuous time version, it's a single rail, but you have to prepare momentum states, which is a little trick here. You have momentum filters in his method. But anyway, that's why running that on a quantum computer is the efficient thing to do. And that is, as I say, not about implementing it physically, but about properties of Hamiltonians that you can efficiently simulate on a quantum computer. However, there is a situation in which you can do a physical quantum walk and have it be universal for quantum computing and efficient as a physical walk. And for that, you need multiple quantum walkers, and they need to interact either at the same or at neighboring sites. So it looks like a spin lattice with many excitations delocalized over the lattice. It's a special case of quantum cellular automata, which were already known to be universal for quantum computing. And there's a nice overview article from Carolina Wiesner here that's available on the archive. The continuous time quantum walk construction that came out in 2013, so like 4 or 5 years later. And if you've got M walkers on L locations, the full Hilbert space is L to the M, and now you can't do an efficient quantum simulation of that. And the experiments that could do this are atoms in optical lattices. So that experiment I mentioned but haven't told you much about yet is the one we want to look at next. But first, just an aside here. Our multiple non-interacting walkers give you quantum particle statistics. So you get bosons or fermions. You have to take into account that quantum particles are not just like ordinary particles. And if you do bosons, you get boson sampling. And it's intermediate between classical and quantum computing and how powerful it is in complexity theory. If you get fermions, you can only have 2 at once if they're starting on the same site, and you can simulate those with entanglement. And there's various papers about how that works too. So here's the simple explanation of quantum walk in an optical lattice. So what we've got is 2 laser beams that are kind of shining into each other, and what you get is a standing wave. And so it's got peaks and troughs, bright and dark patches, and the atoms then are attracted to one or the other, because the potential is different, whether they're in the bright patches or in the dark patches. Now, I've drawn it in one direction, but you can now do it in 3 directions, and then you've got a 3-dimensional egg box trap in which you can put lots of atoms. You can do the coin tosses with unfocused laser pulses that illuminate all of them at once. And you can do the shifts, because depending on the internal state, the coin state, if you put a little beat on it so that the lattice is moving, it will shift the atoms left or right. You need a few tricks to avoid heating the atoms up and losing them. And you need to think about detection, because you can't just image something that's the same as the wavelength of light. But there are ways to expand things so that you can resolve the sites. And you can see it's easy to have multiple walkers, and the atoms can interact in the same site. If you put 2 in one patch, the energy is different than only having 1 there. So that's your interaction. So that's how you would build a quantum cellular automata that will make an efficient quantum computer. So now I'm going to briefly mention a few more less commonly known computing applications of quantum walks. So back to this glued trees algorithm, it's an example of quantum transport, hitting times, where what you're trying to do is cross the graph from one node to another. And there are lots of applications to transport. The first one was actually hitting across a hypercube from Juillet Kempe, predates it by a few months. But it's not a hard problem, because you don't get lost classically on the hypercube. But it did tell you that an exponential speed up was possible for problems that were hard classically. And it also translated into people interested in energy and charge transport in biological molecules. And there are quantum walk models of this. But back to the transport properties, we have the algorithmic evidence of these faster hitting times. But we also have the knowledge that search is essentially Anderson localization, which can prevent even the diffusive spreading. So if you have disorder in the lattice, you don't get transport at all. You get the walk clustering around the disorder points. This is useful if you're searching, though. So here's these quantum wires that I told you about. If you put the input into both of these here, it will deterministically propagate along these wires. If you're using a Grover coin for degree 4, and equal amplitudes on the 2 inputs. And there's reviews, essentially it's the same as spin chain transport, and there is a big review article by Alistair Kay on this. And it turns into, then applies to the idea of perfect state transfer, and there's a nice review article that Tino Tamon and I put together again more than a decade ago now. And there has been work since then to expand and refine the results. There's something else you can do with these ingredients. It's a very computer sciencey problem. We can recognize formal languages if we encode the words in the language into the input of a quantum walk. And then we can set the graph up so that if the walk arrives at a certain site, it tells you whether the word is in the language, and at a different site, it'll tell you it isn't. So a language is a collection of strings of characters. In this case, we've got 2 characters, A and B, and the words in the language all go A, B, A, B, A, B, always like that, starting with an A, followed by a B, followed by an A. Recognizing simple languages can be done by non-universal computers, so small computational devices. And you get equivalence classes of language recognizing computers. And quantum walks can do this. So here's an example. If we want to recognize this language, we can do parallel input. it's a dual rail input, and alpha here is the A, and the 0 is, there's no, not B, and 0 here, but alpha there is the B. So we have A, B, and so on all the way along. And then we join them up with these two bigger Grover vertices. And if it matches up, we'll get to the accepting node. And if not, it will bounce around and never arrive here. And a similar thing happens if we do a serial input. This has got A, B, A, B, A, B. And then we've got accepting and rejecting nodes here. And it always tells you if the word is in the language, but it doesn't always correctly reject. It depends on the word length, how the longer the word, the less likely it is to reject it. But that's common for these devices, is that you have a separation, but it's not perfect. So I'm going to, in view of the time, this is a slightly different version of the serial input. So we're putting A, B in here. So we read it this way, A, B. And then the walk is going to deterministically propagate this way. We've got a delay in here so that we line up the alphas with each other. And then this is the node that's going to tell us if it's in the language. And the propagation keeps going, bounces off the ends, and builds up the amplitude here until it all ends up here, and with certainty we recognize the word. So we can prove it with induction, and this is numerically testing it for the first 200 strings. So these are the words in the language, and then lots of words that are not in the language. So this is work by Katie Barr, who was my PhD student back then. So input words in formal language recognition are encoded classical states, right? What if the input to a language recognizing quantum walk is a quantum state? The task then becomes quantum state discrimination. And you can use quantum walks for this and for generalized measurements. Photonic quantum state discrimination schemes that go back from 2000 and so can be interpreted as quantum walks, because Hadamard's and beam splitters are basically the same operation. So more or less my last slide, this is just giving you the picture of distinguishing between these 4 different quantum states. They're not orthogonal, so you can't do it perfectly. You put your state in here. J is which state we've got. And you can see it will come out of here, or here, or here, or here, depending on which of the 1, 2, 3, 4 it is. And there's another output I haven't drawn here, in that the beam splitters can also have an output this way, and and if it comes out here, so it doesn't reflect here, but it actually comes straight out, that means that we failed at the task. So when we fail, we can also say that we knew that we failed and have to try again. So that was a somewhat eclectic introduction to computing with quantum walks. The takeaway message here is quantum walks are universal for quantum computing. Efficient quantum walk computation is either encoded in qubits or it's multi-walker. And quantum walks can solve a whole diverse variety of problems. I showed you transport problems and formal language recognition. I haven't talked about simulating chiral and edge states, but that's another big area they're used for. And I briefly mentioned search, and I will say a lot more about search next lecture, because I want to use search as a leg up to talking about using quantum walks for optimization problems. So I'm going to, in my next lecture, we're going to use continuous time quantum walks. I will motivate why. And then we're ready to expand to optimization problems in general, which is what we'll cover for the last 2 lectures. So thank you very much.
Are there any questions for Viv?
Thank you for your wonderful lectures. I'm Ada. I have a very naive question. So on slide 20, you mentioned the periodicity of the walk. My question is, what's the significance of periodicity in terms of computation?
In terms of computation, probably not, because it occurs for small sizes. However, it's a very useful property. So what I mean by periodicity is that you set the quantum walk off, and after a number of steps, it comes back to exactly the starting state. So if it does that, that's recurrence, in another word for it in random walk language. It's also very likely then that a pair of nodes then that between which you get perfect state transfer. So that's how that developed into the perfect state transfer work and the transport work. It's a property of the symmetry of the graph it's on. And I think probably Philip Duke's paper and some subsequent ones, it's limited. You either have to design the graphs to have perfect state transfer in some sense. So if I made a loop of those nice chains that we had here, so if I make a loop out of a chain like this, then I can get the walk to just go round and round and round it, right? But that's been designed that way. The number of different types of graph that actually have perfect periodicity or perfect state transfer is quite strongly determined by both the symmetry properties and the way the quantum walk works.
Any more questions? If not, let's thank Viv again.